So dear students, in the fourth part of chromatography lecture, we will discuss two kinds of chromatography techniques. One is the ion exchange chromatography and the second one is the gel permeation chromatography. Both these chromatography techniques are actually example for liquid solid chromatography, where the solid phase is the stationary phase and mobile phase is a liquid. So first we will see what is ion exchange chromatography. So from the term itself, ion exchange, we can understand that there is an exchange is taking place between ions. Okay, so it's a special field of liquid solid chromatography which is applicable for the separation of ionic species. Here, stationary phase is an ion exchanger column. So, an ion exchanger is packed in a column. There are two kinds of ion exchange resins. So, we use an ion exchange resin, and there are two kinds of that. Definitely, we need two because we have two kinds of ions. One is cations and anions. So, one kind is cationic ion exchange resin. The other one is the anionic ion exchange resins. So the cationic ion exchange resin contain acidic functional groups such as SO3H, COOH, etc. So here the acidic hydrogen is exchanging with the ions present in our mixture. So H plus is exchanging for the cations present in our mixture. Okay, so the second type is the anionic ion exchange resins, and these resins contains functional groups such as NH3OH, NH2OH. Okay, so here when we use anionic ion exchange resins, the OH minus group is exchanging with the anions present in our mixture. Okay, so that is the stationary phase. It could be cationic ion exchanger and anionic ion exchanger. Okay, so the mobile phase is a suitable solvent which percolates through the column. The principle is, that is the general principle of any chromatography techniques, that is the different components of the sample mixtures. Here, for example, the ions have different distribution between the two phases. So here, how this different distribution is coming? Because the ion exchange capacity of ions varies. So if you have 5 different kinds of cations, for example, and the efficiency of the ion exchange with H plus ions varies for those cations. So the cation with a higher exchange capacity, that will exchange first with the H plus ion, and that will be in the beginning of the column. Okay, so that's how the separation of the cations taking place. Similarly, the anions as well. Okay, so the principle is different components of the sample mixture have different distribution between the two phases. So the applications of ion exchange chromatography, the first one is the separation of lanthanide ions. Lanthanide Ln3 plus. Generally, we represent lanthanides Ln. So lanthanide 3 plus having highest affinity is held near to the top of the column. So if you have a lanthanide, different lanthanides in your mixture, and the lanthanide which has highest affinity to the resin, or the lanthanide has highest exchange efficiency, that will be held here to the top of the near the top of the column, and partial separation is then effected in the column. So at the end, we are eluting the exchanged cations from the column by using an eluent, for example, citrate buffer. So when you add citrate buffer, the cations exchanged with the resin will get eluted, and the cation with highest efficiency for exchange, that will eluted last, because that will be at the top of the column and that will be eluted last. Okay, so this ion exchange chromatography can be used to separate lanthanides And here you can see the equation. So lanthanide is 3+, so that will exchange with the 3H plus 1 lanthanide ion will exchange with the 3H plus ions in the resin. Okay, then the lanthanide goes to the resin part, and the H plus will go to the mobile phase. And finally, we will add citrate buffer so that the lanthanides attached to the resin will get eluted and that gets separated. Okay, so the second example application is the separation of anions such as Cl minus, Cn minus, SO42 minus, PO43 minus on a basic anion exchange resins. Okay, so you can separate these anions if you use a basic anion exchange resin. Separation of amphoteric ions such as L3+, Zn3+, etc. Then biochemical separations, for example, this can be used for the separation of amino acids, because amino acids you have an amino group and a carboxylic acid group. So there could be a positive as well as negative charge. So you can separate amino acids. Then removal of interfering ions, for example, sulfate and phosphate. If you want to remove some interfering ions, you can use this technique so that these ions get removed from the mixture. Then concentration of traces of an ion in a dilute solution. So it means if you have a mixture where a particular ion is very low in its concentration, so you conduct this separation for different mixture samples so that you will get that ion separated, and you add all those fractions so that you will get a higher concentration of that particular ion. And very importantly, softening of hard water, demineralization of water. So all of you know the water purification system. So most of these water purification system using these ion exchange resins. So if you pass a hard water, so hard water means that contains the carbonates and bicarbonates or sulfates of magnesium and calcium. So the hardness of the water is because of these calcium ions and magnesium ions. And so if you pass this hard water in a cationic ion exchanger, so first it will exchange the magnesium and calcium with the H plus ions from the resin, and then if you pass the water again to an anionic exchanger, that will remove the anions as well, so that you will get the hardness of the water get removed. Or demineralization of water. If your water contains a lot of minerals, means ions, you can also separate those ions by using ion exchange resins. Okay, so these are the applications of ion exchange chromatography. Okay, so we are moving to the second kind of special kind of chromatography technique, which is known as gel permeation chromatography. So actually, this gel permeation chromatography is based on size exclusion principle. So here, the separation of the components in a mixture is taking place because of the difference in their sizes. So that's why it comes under the category size exclusion chromatography. So there are two kinds of size exclusion chromatography. One is the gel filtration chromatography, and the second one is the gel permeation chromatography. So in gel permeation chromatography, which is our focus now, that contains a hydrophobic stationary phase. So you know what the meaning of hydrophobic, water repellent. So that contains a hydrophobic stationary phase, and we use a non-polar mobile phase. And this technique is mainly used to separate the non-polar components in a mixture. Okay, so that is gel permeation chromatography, which we will discuss a little bit more. And gel filtration chromatography is we use a hydrophilic stationary phase, and of course we use a polar mobile phase, for example water. So that's gel filtration chromatography. So we will see what is gel permeation chromatography. So we use a hydrophobic stationary phase. The stationary phase is a solid which is hydrophobic material in gel permeation chromatography. And the important thing is the separation is taking place based on the sizes of the components. So your mixture contains components of varying size. So especially this technique is used to separate the compounds with higher molecular masses, for example, polymers kind of stuffs. Okay, so what is happening is this is a diagrammatic representation of this hydrophobic stationary phase. So what represented here is, so this is an enlarged version of your stationary phase, and what written is pores. So these are pores. Pores are the minute minute holes you can say, or a sponge-like cavities. So that's spores. So that's not visible by our naked eyes. So that's very small. So this material has hydrophobic stationary phase has this kind of pores in it. So, and if your mixture contain, for example, here A, B, C. So if your mixture contain 3 components, A, B, C, and which has different varying sizes. For example, here A is the largest size, and B is the medium, and C is the smallest one. So what will happen is, when a mobile phase containing A, B, C with varying sizes passes through the stationary phase, or which has pores, the smaller molecules can go inside the pores. Okay, for example, here B can go inside this pore because the pore mouth is enough wide to pass B inside the pores, and C, of course, because that is the smallest component in your mixture, so that will also go inside the pore. But look at this component A, which is higher than the pore mouth of this material. So A cannot go inside the pore. So what will happen is, when your mobile phase is traveling through this stationary phase, the A will straight away go with the mobile phase. Okay, so that means you will get A eluted first. First you will get A. So if you look at this result, this is the elution time, and this is the signal of each component. So A comes first, and A has the highest size. A is the biggest molecule. Why it's coming first? Because it cannot go inside the pores of a hydrophobic stationary phase, so it will straight away carried by the mobile phase, and that will get eluted first. Then comes B, because B has the moderate size, so B can go inside the pores, but B is higher size than C. So compared to C, B will come out first, and finally you will get C get eluted. So this is the principle of separation in gel permeation chromatography. So the components are separated based on their sizes. The component with the highest size or bigger size comes first because it cannot go inside the pore of the hydrophobic stationary phase. Okay, so next is the what is the process is happening in gel permeation chromatography. So here I have shown a diagrammatic representation of a gel permeation chromatography technique. So starting from the mobile phase reservoir. So here we keep the mobile phase, for example, toluene or tetrahydrofuran. So these are the non-polar mobile phases normally we use in gel permeation chromatography. So the mobile phase is stored here, and that will first go to a solvent filter to filter any solid particles, because we don't want the impurities to go inside the system. So first we will filter the solvent, then it will pass to a degasser. So degasser is in this mobile phase, in the liquid, there are some trapped gases. So these gases will cause troubles. It can cause air bubbles in the column, or it can affect the accuracy of the detector. So we have to remove the trapped air, for example, oxygen or whatever. So for that, what we'll do is we will pass a inert gas like nitrogen continuously, so that these trapped gases will go out. So that is based on Henry's law. You will study this Henry's law, I think, in your next semester. Okay. So anyhow, after passing to a degasser, then the mobile phase go to a pump, because you have to pass this mobile phase with a little bit of pressure, and somewhere here we apply our sample. So our sample contains our mixture dissolved in a suitable solvent, mainly non-polar solvent. So, and the sample size is like 20 to 200 microliters. So very, very small amount of sample you are injecting here. Then that will pass through the column. So this is our column, which contains a hydrophobic stationary phase. Okay. So the column is placed in a thermostat oven because we need to keep the column in a particular temperature depending on the components in our mixture. So this is our column which contains the hydrophobic stationary phase. So the column is around 30 to 300 centimeter long normally, and 4.5 to 25 millimeter internal diameter. Okay, and if you take one of these particle in the column, which is like it's a porous material, and the pore size is normally less than 10 micrometer, and normally we use polymer particles like polystyrene gel, agarose gels, kind of stuffs. So that packed in this column, and our mobile phase, which contains our sample, will pass through this column, and as I shown in the previous slide, the separation taking place, the bigger particle, they cannot go inside this pore, so they will come out first, followed by the smaller particles. Then after that, those components will reach the detector. So first, the biggest particle will reach the detector. That will give you a signal, followed by the smaller particles. So that's how the separation is happening. So the detector is based on the optical absorbance of the components in your mixture, or conductivity, or viscosity. There are different kinds of detector, so that you will get the signals, the elution time, and a signal for each component. So the first component has the biggest size, followed by the other components. So this is the process what is happening in a gel permeation chromatography. So if you look at the application of gel permeation chromatography, as I mentioned, normally this technique is used in the separation or study of the bigger molecules. So especially that comes in polymer. So in the analysis, characterization and development of natural and synthetic polymers. So for the polymers, the molecular weight distribution is very important. So to know the molecular weight distribution, you can use gel permeation chromatography, or any failure investigation. So reasons for failure of polymers. So suppose if polymer doesn't have the desired properties, then we can analyze why its properties are not up to the mark based on this gel permeation chromatography. Then molecular weight, physical properties, relationships, the relationship between the molecular weight of the synthesized polymer and its physical properties, and quality control, etc. So all this you can done by using gel permeation chromatography. Then in clinical, biochemical, and pharmaceutical research, for example, in the separation of biopolymers like proteins, polysaccharides, and nucleic acids, and analysis of drug products for their purity and stability, etc. Sorry, this is etc. Okay, so you can use in clinical, biochemical, and pharmaceutical research. In toxicological studies, for example, the determination of environmental contaminants like PCBs, polychlorinated biphenyls, or benzoylalpha-pyrene. So PCBs in animal tissues, and benzoylalpha-pyrene in food stuffs. Okay, so these are the main areas where gel permeation chromatography technique can be used. Okay, so in today's lecture, we have discussed two special kinds of chromatography techniques. One is the ion exchange chromatography, and second one is the gel permeation chromatography. Okay, thanks for listening to this lecture.